in the time today, I want to go and tell you a little bit about the scenarios and issues that got us looking at urban water quality and coho mortality and eventually tires and tire rubber. So we'll go a little bit over the discovery process because I think it points toward what systems we should care about and kind of like learning how to think about these systems. And then we'll talk about this guy up here, you know, this compound here, that's 6PPD-Quinone. So we'll go over a little bit about what is it, where does it come from, what are its characteristics, what happens to it in the environment, and where should we pay attention if we care about roadway runoff. So the basic problem really began with observations like this. This is a big, bright, beautiful female coho salmon. Still shiny, probably came in from Puget Sound 2 or 3 days before this video was taken. And starting in the 1990s, Seattle was investing millions of dollars in urban creek restorations, right? They wanted to dechannelize, they wanted to restore habitat, they brought in spawning gravel. You know, they were doing all these things to make sure species like salmon could coexist with people where people were abundant. And that effort in the 1990s really got post-project monitoring teams out in the environment, watching for those fish to see if they were coming back and using the habitat that was created for them. And sure enough, as they do, salmon are resilient. The salmon came back and they were fine until it rained. And then people like Catherine Lynch and Jay Davis and Steve Dam, they'd see the exact same coho salmon they were seeing just fine in their spawning gravel the day before, they'd find them dead downstream. And so those observations really got people out in the field looking for coho salmon during rainstorms, starting in the late 1990s through 2000s, when it became obvious that this was not just a one creek, you know, one storm phenomena, but it was happening throughout the Puget Sound region, you know, multiple watersheds, and subsequent modeling, doing a lot of work by the NOAA National Marine Fisheries Service, found that this was correlated with like roads and traffic and people. But also not correlated with lots of the typical toxicants that kill fish. Things like, you know, ammonia and dissolved oxygen and pathogens and PAHs and metals. So that team worked, you know, for 5 or 10 years at least, trying to understand water quality of this phenomena, and none of the usual suspects were killing these fish. Over time, this became known as, well, it first started out as coho pre-spawn mortality, but really to make it more specific, it became known as urban runoff mortality syndrome. And interestingly, there was already observations that species were disproportionately sensitive to this. Coho salmon would die, and the exact same storms that killed coho salmon, co-present chum and cutthroat trout were not apparently affected, right? So it's already evident that the coho were particularly sensitive to this issue. In some of the most impacted watersheds in the Seattle region, about 90% of the returning coho salmon die prior to spawning from the stormwater toxicity. And that's been consistent. There's at least, you know, I'd say 10 to 20 years of observations like that in those watersheds at this point. So I came to UW in 2014. I'm not going to talk too much about this, but I basically run an environmental mass spectrometry lab. And in particular, I was lucky enough to kind of join this team and start to really dig deeply into the organic contaminants specifically that were co-present during these mortality events using this instrument here, which is a high-resolution mass spectrometer. And the nice thing about this is it tries to tell you what is in the water without you telling it what to look for. So it just tries to report sort of a more unbiased picture of water quality. Pretty much anytime you turn this instrument on, it will see hundreds to many thousands of chemicals in every sample. And so I think of it really as like throwing a big throwing a big net on a tropical reef and scooping up like the 2,000 species of fish there. And so really my team just like looks through that net with like a little flashlight trying to identify all these different species. So picture that just for chemicals, and that's really what we started to try and apply to this problem. And so one of the first things we sort of did is we just tried to see what organic contaminants were present when coho salmon died. And we used a combination of samples that were coming out of some of Jen McIntyre's laboratory toxicology studies where Jen and the NOAA National Marine Fisheries Service researchers had shown that highway runoff from busy highways could recreate like the blood chemistry and the symptomology that was observed in field coho. We also, really importantly, had citizen science teams out in the field call us up anytime they saw a symptomatic fish. So we would jump in the car and grab that water sample. We were really trying to get the water that started to kill the fish. We're trying to get as close to that water that started to kill the fish as possible. And it was really interesting to us. Out of the hundreds to thousands of chemicals that we were detecting in these samples, there were 57 chemicals that were always present when the coho salmon died. So we started to identify them. And over time, we identified about half of them, maybe a little more than half. And lots of them were chemicals that were associated with tires and tire rubber manufacturing. In fact, I think 8 or 9 of the top 10 most abundant chemicals were chemicals coming out of tires. And so this told us a few things. This told us that GIS-based modeling that said that traffic and roads and kind of traffic intensity were factors contributing to this issue, that was now backed up by measuring chemicals in the samples where salmon died. It also really got us thinking a lot about tires as an important source of environmental contaminants. And really, like, everybody here in this room is now focused on the fact that like tires are dumping a lot of contaminants out into the watersheds when it rains. And these are chemicals we should understand better because they're pretty darn abundant. In fact, I had worked on wastewater effluent for a number of years, which is a really common, like, high attention source of environmental contaminants. We were busy in the wastewater effluent systems detecting 5 nanogram per liter and 10 nanogram per liter and 20 nanogram per liter chemicals. In the tire affected runoff systems, we would have to dilute our samples because they were so concentrated they would saturate our detector. And we're seeing things like way up into the microgram per liter, like really high concentrations for environmental contaminants. And this was like, we're like, wow, that's something else. So this got us thinking, and we were also in chemicals we detected that were tire related. We'd look up in the literature and we'd see that they had toxic properties, right? So we started, buying pure standards and giving them to coho salmon, and nothing turned up. The coho weren't dying from the ones we kind of detected in these first years, 2015, 2016, 2017. But by 2017, Jen McIntyre took a tire leachate, and juvenile coho died when she exposed juvenile coho to the tire leachate. And across a whole bunch of other sources of vehicle chemicals like brake fluid and antifreeze and a few other things, motor oil, tire leachate was the only thing that exhibited any toxicity to the coho salmon. So in the fall of 2017, we did this experiment at the Suquamish Tribal Hatchery, the Grover's Creek facility, where this tank here has about 2,000 liters of tire leachate. These blue tubes have socks with like tire particles in them. And we just circulated some well water for 24 hours and then exposed it to coho and chum salmon that had returned to the hatchery. So these are adult, some of those adult chums were big. They were no joke. Just handling them was a feat. I mean, those tubes that have those chum salmon in there, like when that chum salmon flaps its tail, like it wants to take that tube out of your hands. So this is the control with the groundwater, and this is the red arrows have the tire leachate. So this experiment was repeated 4 times. There were 64 adult fish that went into this study. And essentially all of the control fish in the well water for the chum and coho survived. All of the chum salmon that were exposed to tire leachate survived, and all of the coho salmon that were exposed to the tire leachate died in that fall of 2017. So by the fall of 2017, we knew something was really toxic in the tire leachate. Coho salmon could not coexist with it, right? So this problem kind of collapsed into, okay, let's understand tire leachate really well, and let's start to do things like basically a toxicity identification and evaluation process, or an effects-directed analysis. Tire leachate's an incredibly complex mixture. Our instrument typically sees 2,000 to 3,000 feature detections or chemical detections in tire leachate. And what's tricky is a lot of those are closely related chemicals. You know, they're isomers and derivatives and transformation products. So we had to kind of sort through this haystack of like 2,000 or more chemicals to try and figure out which one or ones were accounting for that toxicity in the coho salmon. I always tell people, pay attention to this first line. In a lot of ways, it's the most important line on this slide. We did 27 positive controls where we exposed juvenile coho salmon to tire leachate. That was 135 juvenile coho salmon, and 2 of them were able to survive that exposure. So that really tells you like something that was in those tires is incredibly lethal to coho salmon. Like tires and coho can't coexist, right? Just from that positive control data. In the 125 negative controls, we never had a single mortality. Coho are actually incredibly resistant to chemicals. In fact, like coho salmon were able to survive like, I want to say a 5 or 10% dilution of brake fluid and like, I mean, horrid, horrid water. And it didn't kill them at all. But you put the tires near them and that was it. They were done. So what you see here is just the separation process. I'm not going to go through these steps. This took my postdoc, Zhenyu Tian, pretty much 2.5 years. And there's lots of things we tried and did that don't show up on this figure, right? We chased certain things for months and months and months, and it just didn't work. But at the end of the day, we were able to take that super complex mixture of chemicals that came out of tires, 2,000 things. We tracked the toxicity through various chemical separations, and then we get down to a fraction, a little vial of chemical that started out as tire leachate, but our instrument is only detecting 4 things in it. It's got this little reddish tint, and this killed coho, right? This little 4 chemical fraction killed coho salmon. And so now that collapses like chasing a chemical out of 2,000 to chasing a chemical out of 4. And even of these 4, 2 of them were barely counted as peaks. I mean, they were like maybe not even there, right? So we pretty much collapsed this problem down to understanding this chemical formula. What the heck was C18H22N2O2? We look in the literature, nothing, right? Can't find it anywhere. The regular things that pop up in a Google search kind of don't make sense. So we're looking around for related chemical formulas or transformation products. So we're thinking like one thing's added to the tires and then like in the industrial process, in the environment, it converts to something else, which explains the toxicity. And we see 6PPD, C18H24N2. Most importantly, the carbon and nitrogen are the exact same, right? Because hydrogen and oxygen are easier to change through a transformation type process. And so Zhenyu Tian, he finds a paper from 1983, like an industrial rubber paper. And sure enough, if you take 6PPD, which is called HPPD there, and you react it with ozone, I'll tell you about that in a second, it makes C18H22N2O2. So this was the first clue. This was the day he came in. I forget if he sent an email or came into my office. He's like, I think I know what we're dealing with here. It's like, I think we got this. You know, this makes sense. They put a whole bunch of this 6PPD in tires, and then when it reacts with ozone, it makes that chemical formula we're looking for. So 6PPD, what's it used for? It's an anti-ozonant. Tires are incredibly sensitive to ground level ozone. There's a little bit of ground level ozone in this room right now, right? If you have pollution on a nice sunny day, you have unburnt fuel from your vehicle, you have the paint fumes, you ran your lawnmower, you know, you use some hairspray or something that put some organic contaminants, even pine trees, putting some of those volatile aromatic compounds in the air. In the sunlight, kind of warm, sunny environment, that reacts to create ozone. And ozone breaks down tires and makes these cracks. And this has actually been known since the 1930s. Like in the 1930s, you actually had to wax your car tires. That was to make a physical barrier to prevent the ozone in the air from breaking down the tire rubber. And without an anti-ozonant, like 6PPD, the industry says your tires might only last 1,000 or 2,000 miles. So to get 50 or 80,000 miles, which is, you know, what, like 80 or 100,000 kilometers or more on a set of tires, you need these anti-ozonants. And they work by, 6PPD works by, they mix it into your tires when your tire's manufactured, And then over time, it diffuses up to the surface of your tire, and it basically reacts with the ozone before the ozone can react with the rubber. It probably also makes a little bit of a chemical coating on the outside of the rubber to make almost like a chemical barrier, the same way that that wax used to make a barrier to the ozone getting into the rubber. So what's important is that this compound here, 6-PPD, is added in as an anti-ozonant. When it does its job and it reacts with ozone, it makes 6-PPD-Quinone, right? So finally, we kind of had the chemical we're looking for. We basically bought some industrial 6-PPD. We brought it to the lab. Mike Dodd and his group and Jimin Hu, my PhD student, they ozonated it. Again, the same process that's occurring on the surface of the tire. And it makes C18H22N2O2. And when we put it on our instrument, the retention times are the same, the spectra is the same, everything looked good. We kind of had nailed the chemical identification part of it. And when you actually go and buy a set of tires for your car, you're buying roughly 100 pounds of rubber. You're buying roughly 1 pound of 6-PPD that's mixed into your rubber. So that's the quantity that you physically buy every time you buy a set of tires at the store. That's not an insignificant amount at all. So by this point, it's like late 2019, early 2020. Our final step was evaluating the toxicity of this 6-PPD-Quinone that we made from this industrial 6-PPD. The ozonation mixture was super, 6-PPD itself had some toxicity, but when we ozonated it, its toxicity went way up. And then when we purified the 6-PPD-Quinone out of that ozonation mixture, the toxicity was even higher. I mean, the coho were getting sick and dying, getting sick and starting to die in about an hour and a half. And what's more, it wasn't just like all the chemistry matched up. Jen McIntyre did a whole bunch of blood chemistry studies. The symptoms really matched up, right? So here's an observation in the field. This is the Lower Duwamish River right near downtown Seattle. This is actually the first sick one that I saw in person. It's up on top. It's swimming in that circle. It does that little mouth gaping thing. When we went and made the laboratory 6-PPD-Quinone and we purified it and gave it to some juvenile coho, you can see it was lethal. There are already dead ones in there. But their symptoms also started to match what was seen out in the field in the time scale. So it wasn't just like the chemistry was all matching up. Sorry, I took this cell phone video. It's a little shaky. But the way they behave is exactly like what the adults were doing out in the field. So we had all these chemistry and blood parameters that were telling us we kind of had figured it out. But it was also like just the symptoms and the time scales and just the way everything looked in the system. So that happened just before COVID hit. This was a really exciting day for us who were over in the fish lab doing these studies. I mean, this was the day we really, it was the trial by fire day where we're like, are we right on this thing or not? And they did die. And after that, later that year, we published it all. And eventually, we had to correct our numbers when a commercial standard became available. Our peak area response was biased. But the LC50 that we determined, LC50 is the lethal concentration that kills 50% of the exposed population. We came up with a value of 95 nanograms per liter. That's since been repeated by at least 3 other labs. The USGS lab by Greer et al. Reported 81 nanograms per liter. King County is actually working on, they have a study in progress. They're telling me they have 88 nanograms per liter for an LC50. And then the Canadian study by Lowe et al., who's potentially in the room, I don't know, at least some collaborators are co-present here. Lowe et al. Had a little bit smaller coho salmon. Lowe reported a 41. So we now have 4 studies that are basically, all in that same range, 40 to 100 nanograms per liter. At least 3 of these are probably statistically identical. What's interesting is across a couple groups now, it seems like the most sensitive coho salmon die at about 20 nanograms per liter, somewhere in there, the most sensitive individuals. And yet there are some super coho, like 1% of the population is surviving hundreds and hundreds and hundreds of nanograms per liter. So I think it's also interesting that the response variation within a population is at least 20-fold, right? There's, maybe even 50 to 100-fold, who knows? So coho have a really wide, distribution of responses as well. Like some coho have biochemistry that makes them incredibly resilient to the tire runoff. And if we wanted to just let evolution fix this problem, these super coho are the source of that. So if we waited a few hundred years, these super coho would start to dominate coho populations near humans. And all the coho could maybe survive hundreds of nanogram per liter. But I don't think we're willing to wait hundreds of years to fix salmon, right? Salmon need to be fixed, well, not just salmon. Our water quality needs to be fixed much, much sooner than an evolutionary timescale, that's for sure. And then the EPA at least has a table of the most toxic compounds to aquatic organisms. So again, the lower the LC50 value, the more toxic the chemical is. As far as we can tell, it's entirely possible that 6-PPD-Quinone sits in second place on that list. So it's possible that 6-PP, I've been saying this for 2 years, and I've never had somebody report to me that they knew of an LC50 lower than these values right here. So to the best of my knowledge, 6-PPD-Quinone might be the second most toxic compound to aquatic organisms yet reported. And since 4 of these top 5 are crayfish, it's possible 6-PPD-Quinone in coho salmon is the most toxic chemical known for fish, which is pretty crazy because 13 of the top 15 compounds on this list are hardcore, super toxic organophosphate and organochlorine pesticides, things made to kill biota. And then you have 6-PPD-Quinone sitting in there. And that really tells us, there's a bunch of things we don't know yet about sources of toxicity and mechanisms by which, compounds like quinones can be responsible for such lethality in at least salmonids. By the way, there's also, Marcus and others will talk, there's fish that don't die. The species of fish that seem utterly insensitive to this, like those chum salmon. Okay. So moving on, at least in the United States, 6-PPD-Quinone, as far as we can tell by our analysis, is often present at hundreds of nanograms per liter in roadway runoff from a busy road, right? So you get 2 lanes of road or a bunch of traffic and things like that. We typically see 100, 200, 300, 400, 500 nanogram per liter type concentrations. So the roadway runoff itself is above the LC50 value. So that says if you put coho salmon in an undiluted roadway runoff, they would die because of the presence of the 6-PPD-Quinone there. When you look out in the field, in the creeks where the fish are actually living, you get a lot of dilution, right? There's clean water that's diluting that roadway runoff. And at least in the systems we published on here, concentrations are near or above the LC50 value during storms. So that would tell you that at least some of those fish should be dying in those creeks. And at least in the Seattle creeks, this is Miller Creek, about 60% of the coho salmon die every fall there due to exposure to roadway runoff in the creek. It also tells us that runoff from busy highways might need to be treated by at least 25-fold or so to start to get concentrations, let's say, of 800 or 1,000 nanograms per liter. We need to get those down to 20 or 30 or 40 or something like that before coho salmon can start to survive. And that's also backed up by Jen McIntyre's toxicology studies. She's done a bunch of dilutions. So she'll take roadway runoff from a busy highway and then do a serial dilution. She needs to typically dilute it by at least 20 to 25-fold before the coho salmon start to survive the runoff. So it tells us at least the undiluted highway runoff is well above the LC50. And this also sort of gives a goal for runoff treatment. Like how well do our treatment systems need to work to start to make them safe for the most sensitive biota? So that's sort of what those numbers say. A little bit of an update. Earlier this year, Washington Department of Ecology proposed an 8 nanogram per liter for, I forget exactly what they call it, an action level for 6-PPD-Quinone. I'm not yet sure whether this represents the concentration in the roadway runoff or the receiving water, but it's my belief that this represents a potential regulatory threshold for the roadway runoff effluent, the discharge. So they're proposing this, and it's basically take the LC50 and roughly, take 10% of the LC50 type process. So this is a potential regulatory threshold, a draft regulatory threshold, at least in Washington State. And maybe one way to think about this is Washington Department of Ecology would like treatment and source control to work well enough that we have no more than 8 nanogram per liter in environmental discharge of roadway runoff, to a creek. So what are some places that I'm concerned with? In retrospect, I kind of wish this wasn't called urban runoff mortality syndrome, right? People see urban and they think of like skyscrapers and high rises and, 10,000 people per square mile. In reality, it could be called busy roads mortality syndrome. Because I think if you can intersect a road with a decent amount of traffic in a small watershed without a lot of dilution capacity, which coho salmon in particular love these little small watershed spawning habitats, right? You have an issue. And so you have a lot of cases where there's some sort of roadway runoff pipe. In many cases, this isn't even treated. So there's a lot of scenarios where no stormwater treatment. I do think the DOT here is going to try and put in some sort of treatment system right in this little structure here that then discharges in. But if you have straight runoff from a road like this into a little creek, that's the type of habitat that I think could be quite impaired by roadway runoff and residual tire wear particles and things like that. So these are the types of places that are going to need the most attention. I think if this same highway went over the Columbia River, yeah, it's not good to have toxic compounds there, but the Columbia River would dilute a lot of those, or the Fraser River, right? So at least start with the small creeks. And then anything that's like a sensitive rearing habitat or just a habitat you're really trying to do a good job with. That's probably the place that matters the most. Also, we need to think about where we're putting tires out in the environment. So this is the lower Duwamish River in Seattle. Humans generate a gazillion tires. That's a rough approximation, by the way. It's within an order of magnitude, we generate a gazillion tires. But at least in the 1980s, they thought it was a good idea to use them for erosion control, and they built some tire dikes or embankments, right? And I look at these and I just cringe nowadays. It's like, but even more importantly than the fact that they exist, like I think tires that go wet and dry, right? I'm told there's 1 million tires inside Puget Sound at least, because in the 60s to 80s, they were disposing tires by making what they thought was fish habitat, artificial reefs. I think off of the coast of Florida, there's like 7 million tires that they were dumping out there for habitat. I'm actually a lot less worried about the underwater tires than I am about these like wet and dry ones, because at least in our research, we haven't seen 6PPD-Quinone form underwater, although there's a report or two that says it might in certain conditions. It's these tires that are exposed to that ground level ozone in the atmosphere, and then they get wet from the tidal change or they get rained on. Those are probably the ones that we need to worry about. These tires are old. I think the field is not yet sure how worried we should be about old tires versus tires that are 10 years or less. So understanding like the age structure, like maybe these are fine. Like they're done killing coho. They finished that in the 1990s, right? And here in the 2020s, there's nothing left. But we're going to try and like sample some systems like this and figure that out a little bit more. And then the big question, is if you have $1 million to spend, where do you put it, right? Like we don't have infinite resources. We're not going to treat every roadway runoff site that exists. At least 90% of them are currently untreated. But where do you put your dollars? Where do you put your treatment systems is really important. And even if 6PPD didn't exist, even if they took it out of tires and we completely removed 6PPD-Quinone from the roadway scenario, it would still be a really good idea to have runoff treatment in these systems. Because I can tell you, roadway runoff has a whole bunch of toxic chemicals that they might not kill coho salmon outright, but they're not healthy things for many aquatic organisms to have to survive in, right? And so our busy roads, we should be doing a good job on treatment for them anyways. But at least, we've done some of these studies looking at, like, again, this is Miller Creek. This is kind of our favorite study site. There's a great citizen science group, which is why we work so much on this creek, simply because the citizen science group is there to help us and collect samples and call us up if they see a sick fish, or take care of some fish over the weekend, right? Like, they do a lot of wonderful things to aid our research endeavors. But at least in the Miller Creek system, we think this location right here is actually the spot you'd want to spend your first $1 million on. That little guardrail up there, that's State Route 509. It's basically got 2 lanes going each direction. It's pretty busy, gets a lot of rush hour traffic. There's a pipe sitting up here in the dark. Typically those runoff pipes are completely overgrown with Himalayan blackberry, or they're buried in the bushes. You don't even know they're there most of the time. That pipe collects roadway runoff from about 3/4 of a mile of State Route 509. And I basically think that if a coho salmon can swim above this point, it'll probably be okay. But if it's downstream, there's about 1 mile or 2 of habitat downstream from this point. If it's downstream when it rains, that coho salmon is not likely to survive that storm. And so this is a really good indication of, like, where do you, Site 4A, all those samples right there, we're trying to track that down to exactly where it was, right? That would be a good indication. We need to fix this spot right here. So that's the type of effort that probably has to occur in a lot of little local areas for sensitive watersheds. And then another thing that's a little tricky is here's the concentration of 6-PPD-Quinone. In black is the stream flow, right? So you see that big pulse in Miller Creek, like the creek rises right up in the storm and then it drops back down to base flow. And chemical concentrations kind of start out low and then they can increase by 2 orders of magnitude and then quickly drop off. So I think of, like, this whole roadway runoff, 6-PPD-Quinone space, you're kind of trying to chase a toxic cloud around the environment. And in some watersheds, you might not even get a toxic cloud once a year. Maybe it happens a few times in the fall and never again. Maybe it happens a few times through the year on the right storm with the right dry period. So we have a really tricky problem, because if you collect a grab sample, are you catching it here, 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 or here? The timing of sampling is going to matter a lot. Which storm you go and sample is going to matter a lot. What the preceding conditions and the size of the storm are is all going to matter a lot. So I think we have a lot to learn to how do we actually understand how high did concentrations get, how long a time period where the concentration's elevated. Is there some threshold? Could you get mortality from a low concentration over a long period versus a super sharp, narrow spike? A lot of these questions are not yet known. And so that's where some of the research effort is focused. We see lots. We don't just see 6-PPD and its transformation products. We see other PPDs and other PPD-Quinones in these same systems. So there's a whole family of PPDs and PPD transformation products and PPD-Quinones out there. We think that 6-PPD and 6-PPD-Quinone, they're the most abundant and the most highest frequency of detection, but it's entirely possible that some of these other compounds also contribute some toxicity or toxic character. And even without making the 6-PPD-Quinone, 6-PPD itself is a highly toxic compound. Even before we knew about 6-PPD-Quinone, the safety data sheet for 6-PPD says something like extreme aquatic toxicity or very high aquatic toxicity. So it's really crazy to me to think that we were making tires for many decades with a compound in a class that across the whole class, they say, like, high or extreme aquatic toxicity. And we're putting that, class of PPDs and all their related compounds, some of which have carcinogenic properties and other problematic toxicity characteristics. We're using them not just in tires, but in a bunch of products. And maybe not surprisingly, our environment is full of those. And so that's a good reason that, that runoff treatment is important, even if we kind of eventually tidy up 6-PPD. Really quickly, I'll say a couple things here. Our chemistry data has been saying for a while that we should have mortality in juvenile coho salmon in the spring after they hatch. Most of the focus, at least in the Seattle area and kind of the Puget Sound area, has been on adults in the fall. But our chemistry sometimes has storms that are near or above the LC50 value. And so we're actually working on a study right now to understand the incidence of mortality in juvenile coho in the spring. I happened to see this local article about, I think this Piercy Creek is just north of us, so there was an observation in 2021. I've also had an observation of, by the way, that was about juvenile coho mortality after a rainstorm in the spring, right? I also had another report of juvenile coho mortality in one of the North Vancouver watersheds. You know, one of the little creeks in the lower Fraser had some juvenile mortality. And actually, us in Seattle, we just got some juvenile cohos out on Miller Creek last Wednesday, and the Wednesday night storm killed almost all of them. So now we have, you know, we're definitely seeing some observations of juvenile mortality in the springtime. And in terms of numbers of fish, you know, probably this runoff is killing a lot more fish in the spring, sort of in a, you know, hard to see, harder to detect fashion versus the fall events. So we need to understand what's going on there. I've talked a lot, and I'm going to finish up in a couple minutes here. I've talked a lot about acute mortality in adults. Stormwater, most of this is Jen McIntyre's data, but stormwater exposure makes fish smaller. It affects how their heart works, right? And it affects their lateral line development. So while these acute mortality events of sick and dead fish get lots of human attention, growth and heart function and neural function might actually be more important to the fish even than the acute mortality type things. So I'm really worried about these so-called sublethal effects. And throughout the whole toxic tire chemicals process, by the way, none of these are, we don't think any of these are caused by 6PPD-Quinone, by the way, or 6PPD. These are, most of this is unknown. Probably this is PAHs, but the other one's definitely unknown. So these impacts are really important for us to understand, not just for roadway runoff in general, but also as part of the 6PPD replacement process. I'm going to skip two treatment things other than to say that we do have treatment that works well. This bioinfiltration type system tends to remove about 90% of the 6PPD-Quinone in our systems. Some of the other treatment types, like the cartridge filters, can have really variable removal. Sometimes they don't remove anything at all, as far as we can tell. So we need to do some work on higher performance treatment systems. And we need to figure out where to put those, and but it's probably going to cost some money, right? So like roadway runoff has not been well treated, often because there's a lot of locations. So we need to understand that space and where we put our dollars. We clearly have treatment systems, even with the data we have now, that are pretty darn effective. So we need to make sure we get that green stormwater infrastructure out there in the right places. So these days, these are my eyes. I always say this. Now when I drive around or I travel anywhere, all I stare at is tires and skid marks. And you know, it's just, my eyes are ruined. It's all I can see, especially during a rainstorm. You know, it's just like the space it takes up in my head during rainstorms is incredible. So we need to understand, is it our little cars? Those 18-wheelers with about 2,000 pounds of rubber, they might be generating half or more of the rubber wear on the roads. There's some data that says that. If we electrify our fleet, we might expect 20 to 50% or more rubber on the roads from those high torque electric motors, right? So electric vehicles are going to fix tailpipe emissions, but they might increase tire rubber emissions. And that's why it's even more important for us to understand, what are we doing with all these waste tires, right? They're ending up as crumb rubber on our playing fields, maybe even your shoe soles. Raise your hand if you have a Vibram rubber shoe sole on today, right? I'm not the only one. These compounds aren't just in our tires, right? But they're all around us, like rubber hoses, rubber shoes. I'm sure we could go around this room and find other rubbery little things. And it's entirely likely that they would have, at least some of them, PPD anti-ozonants and anti-degradants mixed into them. But at the end of the day, we need to get to salmon-safe tires that are made with non-toxic chemicals. The tribal elder, I think her name was Joan, started today talking about the way of life. You know, we had to build a way of life. And it really should be the way of life of everybody in this room to get to a point where our tires are made with non-toxic chemicals. Because I think everybody in here recognizes tires end up everywhere out in the environment, right? And because so much of them ends up in water and on wet roads, we need to really, carefully examine the chemicals we're using to make tires and make sure we have non-toxic things that, aren't killing via lethal or sublethal type impacts, the many aquatic organisms, and even potentially humans that are exposed to these things. Since we published, people have detected 6PPD and 6PPD-Quinone kind of ubiquitously in the environment. It's in road runoff and snowmelt and rivers and creeks and roadside soils and rivers and estuary and ocean sediments and house dust and airborne particulate matter. And when people, talk about house dust and airborne particulate matter, that implies human exposure as well. And so a study in China here by Du et al. Reported that they looked at human urine, and they were finding 6PPD and 6PPD-Quinone in 60 to 100% of the human urine samples. And so it's not just fish. We should care about non-toxic tires for multiple reasons, not the least of which we too are highly exposed to these products. So with that, I would like to thank the wonderful people in my lab and many other labs who participated in this research and supported and funded us in some fashion. We had many wonderful collaborators who needed to do a project like this, and I thank them all. Questions? Yeah.